Asutosh, will you please brief about sir?
Dr. S. Senthil Kumar, Professor, Department of Electrical and Electronics Engineering, National Institute of Technology, Tiruchirappalli, India. His qualifications are Bachelor in Engineering in Electrical and Electronics Engineering, Masters in Engineering in Electrical Drives and Control, PhD in Analysis and Control of Capacitor Excited Induction Generators and Power Electronic Converters for standalone and grid connected applications. Sir has an experience of 23 years. He has several research publications and has 9 sponsored projects. Sir has guided 10 PhD scholars and 93 MTech and MS students. The area of interest that includes sir's area of interest include power electronic drives and control, solar PV systems, EV technology. Thank you, sir.
Yes, sir, you can start your presentation. Sir, yeah.
Yes. Very good evening to all of you. Sir, can you able to hear my voice?
Yes, yes, if it is visible and your voice also clear.
Yes, sir. Yes, sir. Good evening to all of you. First of all, I congratulate the management of the institute and Professor Sagu to arrange such an event. Okay. So today my talk is related to the control of power converters for a grid interactive distributed power generation system. Here I'm going to discuss the case studies, whatever we conducted in our laboratory, both for wind energy system and PV system. In fact, most of our PhD students, they worked in the area of PV and wind energy systems, both the standalone and grid connected applications. But most of the controllers, whatever we are using with respect to the standalone, that we are extending for the grid connection. So I just want to discuss a few of our work which we published in IEEE, IET, LCWare, Taylor and Francis. Those work only I just want to show it to you here. So as we know very well, depletion in non-renewable energy sources and concerns of environments. Deterioration have been spurring electric power experts for finding the methods of power generation. Here we can see that some information related to the annual energy supply in metric tons with respect to the various sources of energy. And here we like oil, natural gas, coal, nuclear, like that. And the energy reserves in billion equivalent tons of oil equivalent, that also it is represented. And I'm interested with respect to this slide. So like the emission of CO2 with respect to various sources like coal, oil, natural gas and others. So you can see that everywhere it is there with CO2. The distributed generation in the form of renewable energy sources is believed to provide optimistic solution to reduce the dependency on conventional power generation and mitigate the carbon footprint on the environment. Among the renewable energy sources, wind energy generation system and the solar PV system is very popular due to abundance of energy, installation, flexibility in size. Coming to the challenges with respect to the wind energy conversion system, later I will show you the challenges with respect to the solar PV systems. So we knows very well wind is one of the fastest growing renewable energy sources. So every year we can observe that the wind capacity is increases. Size of the wind turbine is also increases. Size of the electrical machine, which is acting as a generator, that also increased. So with increased and has reached a massive level. The wind energy conversion system has many economic, technological, social, and environmental challenges. The recent advancements for the mitigation of above said challenges must be addressed. The challenges and the trends in wind energy conversion systems are: one is with the potential challenges. With respect to the potential challenges, we need to consider like various factors: the economic, technology, environmental, and the social. When you are representing with the economical aspects, we observed that it is a high installation cost. We need to agree that. But still people are working how to reduce the installation cost. Then technology, power quality issues, short lifetime of the power converter, absence of energy thermal management systems. So with respect to environmental noise pollution, pollution of different birds and bats, accidents, social means accidents and human casualties. Coming to the technological challenges. So one side related to the power converter, the other side is related to the controller. That is a high power density converters. Recently developed devices also people are started to use, like wide band gap devices. It looks to be the compact size and efficient, and it is famous for both EV and renewable energy applications, advanced cooling methods. The MPPT controllers, like fuzzy based MPPT controller, conventional P&O based MPPT controller, artificial based MPPT controller. Sometimes we can go with a mechanical controller also, like a hydraulic controller. Basically, we used to have two back-to-back power converters with respect to the wind energy conversion system. While connecting with the grid, in that case, we can use a different controllers with respect to the inverter side and a grid side, like a field-oriented controller, a direct torque controller, direct power controller, like that. So here a couple of terms we need to be remembered with respect to the wind energy conversion system. The characteristics looks to be the typical characteristics, the power in the wind. I mean the power versus the wind speed characteristics it is represented. It is represented with the three regions, like a region 1, region 2, and a region 3. Here you can see that the end of region 1, it is represented with the cut-in speed, where wind speed, where energy production begins in that particular place only. The cutout speed is in the sense where the wind speed, where energy production ends. After that, the power is constant, that we can observe. Yes. So this point only. So here, and the cutout speed represents with the energy production ends. And we need to understand the performance over the range of tip speed ratios. That is a power coefficient versus the tip speed ratio. One can observe that. The power coefficient, it is not constant for all the value of tip speed ratio. One particular value only it is maximum. So the power in the wind, it is depends upon the tip speed ratio also in addition to the wind velocity. Basically, it is a cube of the wind speed. So coming to the importance of the power electronic controllers for renewable energy systems. For drive applications, let us consider. The input for the power electronic controller is a fixed input voltage, whether it is a AC or DC. The output of the power electronic controller, it is a variable or controllable. That is a controlled output voltage. Whereas for the renewable energy applications, the input is a variable input voltage, AC or DC, and that is output from wind, solar, etc. The output of the power electronic controller is, for isolated system, we require to provide a constant voltage, regulated AC or DC voltage, MPPT control. For grid connected system, a real and a reactive power control, and along with the MPPT control, it is required. Normally, the standalone system, it has to be operated along with the battery. For grid connected system, battery doesn't require, but along with the MPPT control, we could operate. So here, the importance of the components with respect to the wind energy conversion system. So we can observe that the wind rotor, it is fed to the power transmission through gearbox. So here we are getting the mechanical power. That mechanical power, it will be converted to the electrical power with the help of electrical generators. The various types of electrical generators which is available, like a permanent magnet synchronous generator, doubly fed induction generator, screw gauge induction generator, like that. So depends upon the applications, we can choose it. Still large power rated wind turbines, we are preferring with the induction generators only. For small wind turbines and all, we are preferring with the permanent magnet machine, particularly with the synchronous generator. And one can observe that the output of the wind energy directly we can feed it to the isolated loads or grid connected loads through the power converter. So this power converter, it is acting as a power electronic controller. Then it fed to the power transformer, then it is fed to the grid. So that's why this isolated load, it is called as a standalone load. So the power where whatever the power generated, that it is feeding to the grid. So we need to understand the importance of the power electronic converters or power electronic controllers. The input of the power converter is a variable voltage and a variable frequency. The output, it should be the fixed voltage and a fixed frequency. Then only you can be able to parallel with the grid. So coming to the wind turbine concept, in general, the wind turbines are classified into two categories. One is a fixed speed wind turbine, another one is a variable speed wind turbine. Fixed speed wind turbines operates at a constant speed. Multiple stage gearbox we were used. Mechanical stress during gusty wind limits the energy output of the turbine. Synchronous generators, squirrel cage induction generators are employed. The variable speed wind turbine operates at a variable speed, single or two-stage gearbox, possible to incorporate the MPPT, increase the energy output of the turbine. Permanent magnet synchronous generator, doubly fed induction generator, wound rotor induction generators are employed. So coming to the fixed speed generators, Normally, when you are preferring with the conventional synchronous generator, it is basically it is a doubly excited system. One side we can connect it with the infinite bus bar. The another side we can connect it with the field excitation. I mean, the separate excitation is required, but are capable of operating with the lagging and leading power factor. Whereas squirrel cage induction generator, it is very rugged. We cannot compare with any other machine. So synchronization is not required. Singly fed machine, lagging power factor of operation. Capacitors are used for reactive power compensation. And here you can have the idea very clearly. When we are connecting with the grid, the various variable speed generators is there. With respect to the renewable energy sources, whatever you can take with the wind turbine, time to time the wind energy it is going to be vary. So how we are processing that power, power from the generator through power converters, or it is called as a power electronic controllers. For example, if you are preferring with a permanent magnet synchronous generator, we need to have one back-to-back power converter. Through that only we can feed it with the grid. So the power converter, power rating of the power converter is, we need to use with the full rated power electronic converters. Independent control of active and reactive power is also possible. Synchronization problem and the complexity in control. Whereas squirrel cage induction generator, the same thing. Here we are having variable voltage and a variable frequency. So that we need to process with the grid infinite bus bar. So wide variable frequency range for optimal operation. Reactive power compensated by PWM rectifiers. Synchronization problem and the complexity in control. So coming to the third type, wound rotor induction generator, it is one side directly connected to the grid. The another side we are connected with the rotor chopper circuit filter. So this is basically the slip ring induction machine. So it is simple due to the control of single power electronic switch. No power electronic converters at the grid side. So only the duty ratio of the control chopper one is controlling. With that we can inject the maximum value of the power to the grid. In the doubly fed induction generator, you see that the power converters are employed in rotor side. That means the power slip power rating only the rating of the power converters. So the output of the stator is connected to the grid. So it is a slip ring induction machine. The generation is possible both the subsynchronous speed and the supersynchronous speed. Reduced in size of the converters in rotor side. So coming to the fixed speed machine, grid connected induction generator without having the power electronics. One can connect that. Here the voltage and the frequency is constant, then only it is possible to connect with respect to induction generator. When the speed of the machine it is greater than the synchronous speed, considering the frequency of the stator is also constant, then only the generation it is happening. But the important information we can observe that it is a rugged construction, absence of slip rings and brushes, no separate DC source or for excitation and easy maintenance, simple to connect with the grid, the grid synchronization. The steady state analysis we can carry out with respect to the conventional equivalent circuit of the three-phase induction machine, considering the slip alone negative. The important information we need to be observed here is the rated power will be delivered for a slip of about 6% in laboratory size machine and less than 2% for high capacity machines. Sometimes we can connect the capacitor banks at the stator terminal or improving the power factor at the stator. Or we can say that the reactive power compensation. One can observe that the phasor diagram of the induction motor and induction generator. You can see that voltage is taken as the reference phasor in both the cases. The real component of the current is in phase with the voltage in the case of induction motor. The real component of the current is 180 degree out of phase. So that it is generator current. But you can observe that the reactive component of the current both are here. That means the reactive power consumption is there both in the case of generator or motor. So with respect to this, we can observe that the power direction of real power and the reactive power of the both machine and both motor and generator operation. The generator operation, you can observe that the real power feeding to the grid. So you can see that for the operation of induction machines, both as a motor or generator, it requires or consumes large amount of reactive power from the grid. So the another type of generators which is called as a self-excited induction generator. I have indicated one important point like the rated power will be delivered for a slip of about 6% in laboratory size machine. So here voltage and frequency you are keeping as a constant. Then it is not applicable for the variables. And whereas if you want to have the large variation of the speed, we need to allow the variable voltage and variable frequency in this terminal, that is stator terminal. We are connecting with the excitation capacitor and the load. This excitation capacitor will be used for reactive power support to the machine. And the reactive power requirement of the generator and the load are met by the excitation capacitor. The process of self-excitation, it is similar to the conventional DC generator. DC shunt generator. It requires residual flux in the rotor, minimum rotor speed, minimum value of the capacitance. So in general, it is called as a SEIG. For SEIG, both the terminal voltage and the frequency, it is depends upon speed, excitation capacitor, load parameters, generator parameters, like that. In fact, for our undergraduate students and postgraduate students, we used to conduct one experimentation related to the induction generator, like a load test on grid connected induction generator and a load test on isolated induction generator, that is the self-excited induction generator. So observation is a variable voltage and a variable frequency. It is not possible directly connected to the grid, or it is not possible directly connected to the sensitive loads where we are maintaining voltage and frequency is constant. So the frequency and voltage is unknown quantity. It is depends upon the many parameters. So this is what the process of self-excitation. So here the characteristics, it is shown that the air gap voltage versus the magnetizing current. So similar to DC shunt generator, instead of representing resistance line, here we are representing with a reactance line, XC. So when you are decreasing the value of the capacitor, then the line, it will be shifted like this. We can observe that this is the operating region of the self-excited induction generator. The equivalent circuit which we are using for analysis is induction machine along with the excitation capacitor, And the reflected load, that is a grid connected load, how per phase, how it is reflecting, that we can consider as R and L. So then we can consider this equivalent circuit. Here one important information. Here also the slip is negative. The thing is, for given value of the slip, the output voltage and output frequency, it is unknown quantity. For simplification, sometimes we can consider the core, we can neglect the core loss component. So these are the some information like A, which is equal to per unit frequency, and B, which is equal to per unit speed. And how we are converting with respect to the per unit equivalent circuit, that it is represented. For given value of the slip, the voltage and the frequency, it is going to be varied. So if you are maintaining as a constant, then it is called as a fixed speed machine. For effective utilization of the wind turbine, we need to allow the variable frequency at the stator terminal, variable voltage at the stator terminal. So here only we need to show with the importance of the power electronic converter. Here one thing we can say that for given value of slip, the unknown quantities are per unit frequency, per unit speed. For given value of the per unit speed, the A and XM, it is unknown quantity. The voltage is also unknown quantity. So for simulating, we required all these parameters like R1, R2, X1, X2, R, X, XC, then E versus XM characteristics also. So this equivalent circuit, it can be solved by loop current technique or nodal voltages. We can write IZ, which is equal to 0. Under steady state condition, I is not equal to 0. It follows that Z, which is equal to 0. This is a per phase equivalent circuit. Similarly, we can follow with the nodal equation. We can write that EY, which is equal to 0. Under steady state condition, E is not equal to 0. That follows with Y, which is equal to 0. So, in fact, I told you this experimentation done by our student only, BTech students. Here we are conducting an experimentation for calculating the magnetization characteristics of the induction machine. R1, R2, X1, X2 can be obtained experimentally by conducting the conventional blocked rotor test and stator measurement test. So for identifying the E versus XM characteristics, that is the saturation characteristics, the rotor of the induction machine was driven by a separately excited induction machine at a constant speed of 1500 RPM. Since we have 4-pole machine, this being the synchronous speed for the 4-pole machine, under this condition, A, which is equal to B, in the sense anything by 0, infinity, then that component, this part, it will be neglected. So then this is the equivalent circuit. This is what that air gap voltage and input current, whatever we are having, that it is the magnetizing. So at this speed setting, the stator is fed from the variable voltage source at a rated frequency. The input current and power are measured for each value of the input voltage. Then XM and air gap voltages at various input voltages can be calculated. So like this, the stator voltage and the stator current, it has to be estimated. Actually, many literatures, if you are referring, many optimization techniques also applicable. Very recently, one of our students, he has developed a simplified method like a binary search algorithm he has used. And this is the characteristics with respect to the machine side. Like when you are loading the machine, unity power factor load, which we are connecting at the stator terminal, that is R index, it is a reflector. When the load on the machine it is increases, the voltage it is going to be reduces, similar to the DC shunt generator. When the load is increases, the load current is also going to be increases. And the stator current is the combination of the capacitor current and the load current. So this represents the stator current. And this has been tested with both the 0.8 power factor lagging and the unity power factor. Basically, it is the machine is around 4 kilowatt machine, this one. We can see that more than 4 kilowatt only the saturation is occurs. But here 0.8 lagging, we are not able to load more than 1.8 kilowatt. This is for your information. I told you that the self-excited induction generator, the output voltage and the frequency, it is going to be varied when you are varying the speed. Even if you are keeping the speed of the rotor is constant, the frequency of the terminal voltage, it is going to be varied when you are varying the load. So that this is what the characteristics by considering the speed of the machine is constant this much, and the excitation capacitor we were consider is this much. So how the frequency it is going to be varied, and magnetizing component also, XM also how it is varying, those things we can see here. And this is the magnetizing inductance with respect to the air gap voltage, it is how it is varying. So normally we used to find it out this characteristics only it is useful for the simulation. And simulation and experimental results with respect to the generator alone. Still we are not going with the power electronics. So this is what the generator, this is the instant at which 1 second we are closing the capacitor. The generator voltage and the generator stator line current, how it is developed, that it is shown here. And here this is the no load operation. At 1 second we are closing the the excitation capacitor. You see that the generator rotor speed it is going to be reduces, and the terminal voltage it is going to be developed, the stator current is there. Then magnetizing inductance also it is going to be varied. Then the stator frequency also it will be changed. So this is represents with the stable operation. At 3 seconds we were connected with some load. The voltage it is going to be reduces. Stator current is also going to be reduces. But the generator speed also it is going to be varied. Then magnetizing inductance also it is going to be varied. Then generator stator frequency is also going to be varied. Before completing the process, for example, instead of operating with a 3 second, one is operating at 1.2 second itself, the load is connected. Then what it will happen, the self-excitation will be collapsed. That only we are calling as an unstable operation. In fact, we tested parallel operations, everything. This is a fundamental information with respect to the generator. Now, any discussion at this stage, you please ask me. I have discussed only the wind turbine, that generator. If no discussion, I can move for the next level. One is connecting, I said that directly without having the power electronics, one can connect with the AC grid. The effective utilization, it is not at all possible. That is MPPT, not at all possible. The power converters are needed to be interfaced between the stator terminals and the AC grid for wide speed operation to achieve MPPT. So that means here the power electronics is very much essential. This power electronic converters, it may be the single stage or two stage. So that means the input for the power electronic converter is the variable voltage and variable frequency. The output is a fixed voltage and a fixed frequency. The SEIG, I mean, will operate in wide range of rotational speed for achieving the MPP. So like various configurations which is available, like a diode bridge followed by the line commutator converter. MPPT algorithm is possible. More harmonics at a generator and a grid terminals. Control is very simple. And here normally line commutator inverters are connected with the SCS. So there are otherwise one who want to improve the power quality aspects. Instead of using with diode bridge and a line commutator in converters, we can go with the PWM converter and a PWM inverter connected with the grid. Then here also the MPPT is possible. Very low value of harmonics generated at the grid terminal. Reactive power control is also possible and the control is also complex. So the MPPT algorithm employed for extracting the maximum power available in the wind. It is based on the mechanical parameter or electrical parameter. Tip speed ratio versus control, optimum relations based control, that is curve tracing from power versus speed or power versus star, or we can have the perturb and observe control. So most of the places we are using with P and O, since it is very fast and it is very simplicity and reliability. For isolated system, the MPPT is possible if the dump load or energy storage devices are included. So this is the one of the configurations which we connected with the battery. The power output in the wind turbine directly connected to the battery. In this regard, the first stage we need to have diode bridge followed by this one. And based on the power requirement of the battery, the remaining power, it has to be fed to the dump load. That means it has to be wasted. So here the MPPT algorithm does not require the optimum power characteristics and measurement of the rotor speed. So less complex and low cost. And instead of this, whatever the power which is available, that we can feed it to the grid. In this regard, people were applied with the pitch control also. And how it is feeding to the DC microgrid and a battery, that it has been available in the literature. Now we can see that once again, the typical characteristics like cut-in speed. I told you in the beginning itself what is cut-in speed, what is cut-out speed, what is the rated speed. So this is what the cubic characteristics. The power in the wind is directly proportional to the cube of the wind speed. And here only we can have the generator control. So this is the operating region. But here we can have the stall or pitch control since the power is constant. Once it is reaches, the power is constant. So the entire control is here only. And one who wants to connect with the standalone applications. In fact, we tested with the IGBT based power converter. This with the stretch we were started in our laboratory. So this is this work. Here we can have it variable voltage and variable frequency. And here we can, whatever the power which we are feeding to the battery. This power converter looks to be the semi-converter. This power converter looks to be the semi-converter, IGBT based semi-converter. The reactive power requirement for the generator is fed by the capacitor, and whatever the power which is available, that power we are feeding to the battery. This power converter we were tested with the conventional firing angle control schemes, like extension angle control scheme, symmetrical angle control schemes. Then one more firing angles control schemes we were called as a negative firing angle control scheme. So then phase angle control schemes. This is the typical characteristics, typical waveforms with respect to various control schemes. We were tested with respect to the generator and analyzed. And we were observed that the load power, I mean the battery power, we were considered with the 2000 watts and 1000 watts. Under that case, different firing angle schemes we were applied. And whether the power 200 amperes, 200 volt 10 amperes or 100 volt 20 amperes, under that condition, the symmetrical angle control schemes, you see that it provides the same quantity. So similarly, 1000 watts also, 200 volt 5 amperes and 100 volt 10 amperes also it is providing. This is what the constant speed operation we were conducted the case study. So under that condition, how the stator voltage, stator current with respect to different control schemes, those things we were evaluated both theoretically with respect to the generator characteristics, like a stator line voltage, stator line current, a power output like that. And how it is reflected the control schemes, like the conventional symmetrical angle control scheme. It will provide the unity power factor at the converter input terminal with respect to the fundamental quantity. And extension angle control, it will provide the leading power factor. That means the reactive power needed for the machine. It will be supports. And in a negative firing angle also, it will be operated with the leading power factor. Whereas phase angle control, it will be operated with the lagging power factor. How it is reflected, whether it is a resistive nature or reactive nature or RL nature, those things we were validated. So with respect to the variable speed operation also, we were tested variable speed with a constant load power. This is not possible with respect to the realistic condition, but since we are employed a prime mover is a DC shunt motor in our DC machine lab, machinery lab, with that we were tested. So how it will be the stator voltage and the stator current for each control schemes we were verified both theoretically and experimentally. So with respect to the wind energy conversion system, this equation we were discussed in the beginning. The power output in the wind turbine is directly proportional to the cube of the wind speed. So this is what your generator control. With respect to different controls applied to the power electronics, like symmetrical angle control, extension angle control, negative firing angle control, we can obtain the variable speed up to this range. So this is what we can switch the control from symmetrical angle control to extension angle control to negative firing angle control. So that means the effective utilization we can use up to this. This is what our conclusion. So this is the simulation and experimental waveforms with respect to the various points like stator voltage, stator current, capacitor current, load current, load voltage, everything we measured both theoretically and experimentally. This work has been published in IET electric power components and systems. Electric power applications. One of the PhD student worked in this area. His name is Karthikeyan. Right now he is working as a faculty at PSNA Engineering College at Tindikkal. And the same work we were extended for AC loads and microgrid operation along with the battery. We were used with the hybrid exciter. Here we see that instead of connecting with the DC load, we were connected with the AC load. But we are considering here voltage and frequency we were maintained almost constant. So how much range we were using instead of capacitor bank? We were, in addition, we were used with one battery bank along with the AC and AC to DC, DC to AC power converter. So this power converter, it is operated in open loop only. And based on the battery voltage and here whatever the voltage which we required in this point, we are going to be maintained and a constant, and a frequency also it will be maintained constant. That means here voltage and frequency it is maintained constant. So the possible cases of operation is when the power generation is less than the load power, what it will happen, the battery it will be supplied. When the power generation is greater than the load power, the excess power it will be fed to the battery. When the generated power which is equal to load power, the power exchange between the exciter system and load which is equal to 0. This is very, very simple control. This work is also published in IET Renewable Energy. So this work is also carried out by one of the PhD scholar. Right now he is working as a associate professor at NIT Surathkal, Karnataka. And this is another work with respect to the DC load. Here we are maintaining constant voltage at the DC terminal. The input voltage we were considered as a variable voltage and a variable frequency. So basically it is a PWM rectifier. Whatever the disadvantage we observed from the semi-converter is the harmonics is present in this terminal. That harmonics we can eliminate with the help of PWM rectifier instead of using the line commutated rectifiers. So the PFC controller we can adapt here. Like the DC voltage, it will be maintained a constant with respect to outer loop controller. The inner loop current controller, it is going to be maintained with the current shaping, sinusoidal current shaping. Then we can claim the important advantages a derating of the machine. While connecting with the conventional line commutated converter, we have the derating, whereas here the derating will not be there. So this work was carried out by one of our MTech scholar. This controller has been developed completely in operational amplifier. Within 500 rupees, he has developed everything. And he tested with the initially breadboard. Later, he made it with PCB. So this is what that analog-based two-loop control scheme. The first stage he has represented with a proportional integral controller. This is for responsible for DC voltage maintaining. And the second stage, it is for current controller. So that means the output of the voltage which is equal to current magnitude of the first controller. And we need to make it as a shape. So for that, we have the one multiplier. So that multiplier, it will multiplies with the current. That it is very clear here. So that is the voltage magnitude, unity magnitude of the voltage shape, it has to be multiplied. Then we are making with the current reference. Then the actual current in the converter input terminal, it has been measured and it will be fed to the controller. That controller, it may be the hysteresis controller. Since hysteresis controller, it is called as a schematic trigger. Implementation of the schematic trigger with the operational amplifier is so simple. That's why he has chosen operational amplifier. This is what the schematic trigger circuit. So then he has developed the pulses for upper and bottom switch of one leg. Similarly, we can make it with the second leg and the third leg. So right now he is working in the EV industry. The work which he this work carried out by one of the PG student. I told you his name is Mahendra. And the various performance characteristics also here also we observed like constant speed, variable power operation, variable speed, constant power operation like that. Everywhere we tested with the generator characteristics. The generator characteristics as per the theory which we discussed. And the same thing, theoretically we were validated, simulation also we were validated. And this work was published in IET Generation, Transmission and Distribution. So how we are maintaining the sinusoidal current shaping, constant DC voltage, those things it will be there. But one of the reviewer and the power quality also we were checked. It looks to be less than 5% as per the standard. Similarly, variable speed operation also we carried out like 1500 to 1400 RPM, 1400 to 1500 RPM like that. And one of the reviewer for this work, he asked us to make it the simultaneously changes from the speed and the load like 1400 to 1500 RPM, 1.7 kilowatt to 1 kilowatt, how it is happening, whether the DC voltage is maintaining constant and sinusoidal current shaping is maintained, unity power factor were achieved. Those things he asked us to evaluate. And the same controller we were tested with respect to the wind turbine available in our department. So very recently we removed for certain issues this wind turbine. We thought of installing in the ground level instead of terrace. So we tested the same thing at one particular operating condition. We tested the load voltage is maintaining constant, that is this one, the load current and PWM rectifier input current like this. And the same work is extended for with respect to instead of analog controller, we were applied with a digital controller. So the digital power controller we were applied. Like conventional power control schemes also we were developed with respect to the FPGA board. And this is the DC it is a DC link voltage we were maintained as a constant. This is the inner loop current controller. So this is the decoupled control strategy we were brought for the SEIG. So this work was carried out by the one of the PhD student. Right now, she is working as a principal in Government Polytechnic College, Maharashtra. She done her PhD under QAP program. This work was published in IET Power Electronics. So this is for your information. And she tested with the D-Space board also. This is the inductors we were connected with external inductors and a PWM rectifier, a D-Space. So everything is there. And she tested the dynamic response of the system, like a step change in load, how we are maintaining the current shaping, DC load voltage, how it is maintaining constant. So even with the transient conditions also, and a variable speed operations also she tested. And one more candidate, like extension of this work, we tested with respect to the real and reactive power control in PWM converter system. Like anyway, we implemented in digital. The drawback of analog controller, we brought it. And ID and IQ control, we brought it. So the unity power factor control, how we were achieved. Lagging power factor control, how we were achieved. And the leading power factor control, how we were achieved. Those things we were explored. So this work was carried out by one of the PhD student, Mr. Dr. Subani. Right now, he is working in the EV industry. So here he observed that the current which is getting leading as per the requirement of the reactive power for the machine. That means the converter, it is going to be supplied with the reactive power. So the same work which was extended by one more PhD student, his name is Nayana. So he was working with our department. The same work only, the PWM rectifier, and he has connected with the DC grid. So he made it with a single sensing only. So this work was published in uh, uh, IEEE transactions on power electronics. This is for your information. So here he has connected with the transformer, and this is what one more work. He has a schematic diagram for the system with respect to the DC load also he can make it. So instead of this, he has used with the step down DC load voltage, because this configuration will provide step up DC voltage only. For that only he has used with the transformer. And this configuration is, of course, here everywhere we are considering with the variable voltage and variable frequency. So the same sensing we were using, and how it has been fed with the DC load, the same controller developed by earlier student. Like I told one of the student, a QAP student, right now is working with the principal at Maharashtra state. So our work only extended here. So this is what the current loop and the voltage loop. Everywhere this work was published in Taylor and Francis. So the journal name Energy Sources Party Journal. And of course, with respect to the different frames also, we were explored in our research, like a stationary reference frame, arbitrary reference frame, synchronously rotating reference frame, like that. Most of the cases we are preferring with the synchronously rotating reference frame, since the control it is very simple. So these are the fundamentals are related to that. And when you are going with the stationary rotating reference, stationary frame to synchronously rotating reference frame, everywhere the power it should be constant. That only we were observed with respect to, that means the control implementation is easy in synchronously rotating reference frame, as all the quantities are in DC, and power is invariant irrespective of the reference frame. So actually this particular slide, I mean the DQ slides were effect of harmonics, those things and all developed by, this work was carried out by Professor Asha Rani. Right now, she was also carried out a PhD in our institute. Right now, she is working in as a faculty at NIT Tiruchirappalli. And the performance analysis also we carried out. Since the output voltage and the frequency, it is a variable. XM is also variable. That is, for given value of the speed, the nearly three quantities are variable quantity. We need to compute. In this regard, we were applied initially PSO, then genetic algorithm. Then very recently, we were applied with binary search algorithm. And we were tested with respect to the performance analysis, how the XM is varied, what is happening, the reflected frequency, reactance, resistance, frequency, air gap voltage, what is happening. Those analysis we were carried out. And the steady state response also we were found with respect to the 1 kilowatt system, how it will be. And transient results also we were observed. And simultaneously changes also we were observed. And the same work we were extended for grid connection. So this is overall schematic of the grid connection. The front end, we were connected with the diode bridge, and grid side only the connector we were connected. I mean the controller we were connected, voltage source converter. So whatever the may be the wind power, based on that, we need to inject the current at the grid terminal. Since here voltage and frequency is constant, here the voltage and frequency it is variable. We are processing the power. In this regard, this work is also carried out by the one of the PG student. So right now he is working in the power industry only. So here, based on this control scheme, he has developed the three-phase control scheme only. The current reference he has made with respect to the available speed. So that means based on the operating speed, the speed it will be converted to the voltage that it will be feed as here to make it as a MPPT operation of this. Then the actual current and the reference current it has been compared and it fed to the controller, then feed it to the gate driver unit. Then we were tested the generator performance at the grid terminal. So this is what the capacitor excited induction generator, a DBR and inverter by considering the constant speed of 1 per unit. So the variation of the stator voltage and the current against the output power it is shown. And how it is follows similar to the generator characteristics that we were tested both experimentally and calculated values. So everywhere all the values are matching. And this is what the experimental validation, like a sudden increase in real power to the microgrid. We were considering from 1 kilowatt to 2 kilowatt and 2 kilowatt to 1 kilowatt, whether we are able to maintain the sinusoidal shaping of the current at the grid terminal or not. So since the diode bridge rectifier we were used and the DC link voltage, it will be continuously, it will be varying. And the power quality also we were tested with the grid terminal, but the drawback is the power quality, it will not be there at the generator terminal. One is using with the back-to-back power converter, definitely the power quality it is going to be improved. So this is the, by considering the constant injected power of 1 kilowatt and by varying the speed, so we were tested with the stator current, stator voltage and load line current, that is a back-to-back power converter input current. So those things we were validated. Theory and experimentation both are matching. And we were able to maintain the MPPT operations also. This work also published in IET Generation, Transmission and Distribution. This is for your kind information. And we were tested with respect to the real wind situations also, that is a cube of the wind speed. When the power is changing, when the wind speed is changing, how the power it is going to be changed. So how much the power it is going to be injected. That is a theory and the experimental readings we were observed, that also it is given here. And the corresponding stator voltage, stator current, everything we were tested. The corresponding experimental waveforms also it is explored here. And coming to up to this stage, any discussion is required, you please. If no discussion, I just want to discuss in general the structure of the distributed power generation system. It looks to be like the input power, it may be from wind, solar or fuel cell. The output, it will be connected to the utility grid or local load. So the overall control unit, it may be the input power control, MPPT control, generator speed control, and sometimes we can have it the grid monitoring, grid synchronization, line impedance detection, like that input side controller, grid side controller, like that we can separate it. With respect to the distributed power generation system in general, we can again, I just want to repeat it here, extract the maximum power from the input source. Grid side controller, grid synchronization, control of active power generated at the grid, control of the reactive power transfer between the distributed power generation systems to the grid, ensure the high quality of the injected power. But sometimes we are not having the control of the DC link voltage. So when you are referring with respect to the fundamentals, the power flow control. So the energy transfer and the power flow between the AC terminals and the grid connected power converter mainly depends upon the relative phase angle. So this phase angle depends on two absolute angles. To control the grid connected power converter needs to estimate the AC voltage phase angle in order to set the switching firing. So in this regard, the hysteresis controller only we were using for reference value generation, particularly the current controller. So here we can see that the power converter and the controller, that is how it is acting. The grid connected power converter needs to track non-DC references, which makes the design is complex. So this is the representation with respect to the single phase operation. This is the one of the experiment we've used to conduct for our MTech students. So here one H bridge is there. That H bridge, how it is connected to the grid. Input side is a DC. And a pulse generation, it will be there. How much current we are going to be injected at the grid terminal, that it is depends upon the reference. So that is 1 by X is decides. So where V represents the unity magnitude, and we can extend the same thing with respect to the DQ controller also. Actually, with respect to the solar PV system, many type of inverters which is available, like a central inverters, string inverter, module inverter, like that. So everywhere we want to bring with high efficiency. This is our motivation of the research. So mini and central PV inverters are also emerging for modular configuration in medium high power configuration. So these are the some structures like transformer based structure with respect to the low frequency side, that is a grid side, this one. And high frequency side also we can have it, then the size it will be compact. So efficiency we can, this and all it is available in the existing literatures. So sometimes we can have it without using the transformers also. So we can bring it with more than 95% of the efficiency like that. So with the transformer is also available, and without transformer is also available. How it will be the efficiency with respect to the transformer less low frequency transformer and high frequency transformer implementation. So definitely the weight and volume it has to be reduces with respect to the high frequency isolation instead of low frequency isolation. And the efficiency also we can improve it further. So these are a few slides we used to discuss for our students, how we are going to be generated with respect to the PWM, everything. Because again, the slides are repeating. Yeah. So coming to the grid synchronization techniques. So in this regard, one who wants to control digitally, like decoupled power control, you require the synchronization techniques. Since the input voltage and input frequency of the power converter is a variable voltage, variable frequency, output you need to be maintained as a constant. So in this regard, we can have the open loop method like ABC to DQ alpha beta frame. We can have it with sin theta and cos theta. The closed loop method of PLL is widely used for the synchronization algorithm. Basically, the phase locked loop only we were using for estimating the sin theta and cos theta. The zero crossing detector based PLL, it looks to be very simple, and phase detection is possible only at zero crossing points. So sometimes we can use with a reference frame based PLL. One who wants to have wide range of operation. It is widely used as satisfactory performance under balanced condition. Poor performance under unbalanced condition. So this is what the structure of the basic three-phase PLL, like a phase detector, loop filter, voltage control oscillators. From that only we are having the theta, like a ABC to alpha beta to DQ. Then we are inserting with one loop filter. So from that we are having the frequency. From the frequency only we are having the theta. So here one of our student, right now he is working as a professor at VIT Vellore. His name is Dr. Aravind. He pursued a PhD at NIT Tiruchirappalli. He has carried out this work. The effect of utility distortion on the PLL performance. So he has considered with indexing like unbalance, harmonics, DC offset, phase jump like that. So here he has considered that how it will be the effect. The unbalance he has created with respect to the phase A terminal, the corresponding VD and VQ is represented. Here you can see that the shape of the VD and the VQ, definitely the theta it is going to be changed. The control rate will be not with respect to the expected. And he tested with by introducing the harmonics also. Like a fifth and seventh harmonics he has introduced with respect to the each phase. Then he tested. So then he observed that VD and VQ, how it will be. Definitely the theta is not estimated as per our requirement. In this regard, we are not able to maintain the power quality at the grid. Similarly, the DC offset, he has added at the phase A, and the corresponding VD and VQ is also observed. It is not uniform. The phase jump also he has introduced. And with respect to that also he has tested. So we were observed that the effect of distortion on DQ frame is unbalanced, harmonics, the DC offset, phase jump like that. So the corresponding ripple frequency, how much it will be, that also we check. One is going with the SRF PLL. The output like ABC to alpha beta to DQ. Then we were having one controller. Then we are estimating with the theta. So now when you are making with unbalanced, you can see that balanced, you are getting clearly. When it is unbalanced, it is not proper. It looks to be the fast transient response under balanced and distorted conditions. But a distorted output under non-ideal conditions, steady state error, under frequency deviations. So instead of that, one low pass filter were introduced by one of the literature. we were observed that improved filtering characteristics under distorted condition, slow transient response, steady state error under frequency deviations. We observed that this is the filtering characteristics, bandwidth of the filter. So one is reducing this bandwidth, how the filter characteristics, that means when the bandwidth is increasing, the filter characteristics, it is going to be reduces. And one more in this regard, one more author, he has developed the same PLL by introducing the notch. So with respect to that improved transient response, the steady state error under frequency deviation is also not there. And one more researcher, Rakesh Kumar et al. And Sen Sharma from IIT Kanpur, they developed a pre-filter based PLL. So we observed that a good filtering characteristics under distorted conditions, improved transient response under distorted conditions. They developed 5 stages, but a slow response under frequency deviations. So decoupled double synchronous reference frame PLL also were developed by one of the researcher. And we observed that a distorted under harmonic conditions. Then adaptive linear optimal filter based also one researcher were developed. So we observed that a computational load depends on the number of harmonics were considered. So EPLL also developed, but the difficulty in implementing practically that we were observed. So the observation is a state feedback loop tracks the phase angle and frequency. Forward frequency, it must be kept constant, increased complexity in phase detection. Poor performance for large frequency deviations unless a compromise is made for filtering characteristics under distorted conditions. The requirement is a fast transient response and good filtering characteristics under distorted conditions. Zero steady state error and improved dynamic response under larger deviations. So in this regard, we observed that one FIR filter were introduced, and along with that, we were introduced one feed forward. So with the feed forward, we are meeting all the indexing, like improving the filtering characteristics under distorted conditions, improved transient response, a faster response under frequency deviations. So the same test system has been tested with respect to the PV, like a PV, one boost converter and a inverter. And here response of the PLL at a startup. So that means a balanced condition. This is the simulated results. This is the experimental results. So this is the cos theta. This is the theta. So at startup, both the theory and experimentations is matching. So response of the PLL under unbalanced conditions, we were tested. The unbalance is created here. So in this point only we were created. With respect to that, we were, by applying our proposed technique only, we are able to get the cos theta properly, even though when it is unbalancing. So when we were applying the harmonics also, the cos theta we were getting properly by introducing 5th harmonics and the 7th harmonic. So by adding the DC offset also, we are able to get properly the value of the cos theta signal. And phase jump also we were tested. Then the response of the FPLL with step change in the frequency with the distorted conditions also we were tested. So likewise, we were tested the power quality. Further, we were extended the same work with respect to the grid interface with respect to battery charging. And this is the one of the power converter scheme developed by our PG student. So input side is the battery, output side is the grid. So how he has maintaining the constant voltage control, those things he has explored. And he has used with the hysteresis current control schemes only. So how the power converter it is operating as a STATCOM, that also he has explained, like a rectifier operation, inverter operation, with respect to how the power flow, reactive power flow, real power flow in both the direction, different direction, simultaneous direction. So here he has adapted with a single phase PLM. This work was carried out by one of the PhD student right now, and he is working as a faculty at Rajiv Gandhi Institute, Basar, Telangana. His name is Rakesh. He tested how the power flow with respect to the rectifier operation and inverter operation. So he tested the power quality. These are the various testing operations. And both experimentally also he tested. These are the few references. I think I have taken more time. Any discussion, you please.
Participants, any questions? Chat box also you can ask.
Sir, good evening, sir. This is Kandasamy.
Yes, sir. Please, sir.
Just actually, you showed in one of the slide that is a two loop current control in analog and digital, right?
Yes, sir.
Sir, actually, my doubt is which one is advantage, sir? More advantage, whether it's analog control is better or digital control is better? Because in most of the journals, if you send it some type of digital type of control, they are not preferring rather than analog control, right, sir? So,
yes.
which one will be preferred, sir?
Actually, to be frank, digital only good.
Okay.
The thing is, digital only, whatever the control you can implement very easily. Whereas analog, the particular student is very, he is very much interested to work in operational amplifier. That's why he has developed with the analog controller. He has explored. So we can develop the three-phase controller with operational amplifier itself. But whatever the control flexibility, if you want, better you to go with the digital controllers, with the digital hardware, with any of the processors like FPGA or embedded processor, DSP, anything.
Okay. But the transactions, which one they will prefer, sir? Whether analog or digital, sir? The general purpose.
Sir, that is depends upon the work, sir.
Okay.
Actually, what the work which we are proposing, whether you are implementing in analog or digital, doesn't matter. The work which you are proposing.
Okay.
And under which environment it is used. Actually, that work, that particular work is with cost-effective controller we were developed. That's all.
Okay, sir. Okay.
So that only we were projected, but he faced a lot of issues. So, for example, the first stage of operational amplifier, it will create some offset problem. So you want to adjust with respect to that along with the second stage. So that problem he faced, but at the end he succeeded.
Okay.
But a single loop, I mean, instead of two loop, suppose the single loop is there, analog is much better compared to the digital.
Okay, sir.
So if you want to control only one parameter, then you can go with analog. That is sufficient.
Okay, sir.
If you want to control multiple parameters, definitely the digital hardware is very much essential.
Okay, sir. Okay, sir. Thank you so much.
Okay, sir. Actually, one of the participant he expected with the EV, the same controller whatever we developed, we were extended for the EV also. Very recently, whatever we are developing the power converter controllers, that we are extending for the EV operation, like grid to vehicle operation, vehicle to grid operation, like that, vehicle to home. So these operations we were exploring. So the present PhD students, those they are working in this area.
So, are there any questions? So will I wind up the session? Okay, sir,
Sir, one participant asked that can you share any research gap left to go through with regard this topic? Definitely is there. With respect to the wind energy conversion system, still people are expecting with a compact controller with respect to the variable speed operation under various power quality issues when we were connecting with the grid. Already many literatures are available, but people are expecting with the compact control techniques. Since we are not going to change with the turbine or generator or power converter, if you want to explore, you can explore with the type of power converter which you are going to use. The same way you can extend for the solar PV systems also.
so sir, we will wind up the session, sir. So thank you very much, sir, for your broad research area from maybe basic power converter to drive so many other things. So we have presented over here. Thank you very much, sir.
Thank you, sir.
And participants, further if you have any doubt or engage NIT Tiruchirappalli websites or email ID and details are there. So he's very humble person. Anytime we can contact him.
Okay, sir. Thank you, sir. Thank you so much.
Thank you, sir.